In this video, I'm going to explain you about this. So we have here, if A and B are finite dimensional subspace of a vector space V, then since A and B are finite, A plus B is also a finite dimensional vector space. Then we have to show this, okay? So I have already proved this one in the previous video of mine. I have already proved about this isomorphism, that is A plus B by B is isomorphic to A by A intersection B. Now both are finite dimension, A and B are finite dimension, so A plus B is also a finite dimension, as well as A intersection B is also a finite dimension. So this side is a finite dimension, so we can take dimension of this. Since these two vector space are isomorphic, the dimension of this and dimension of this will be same. Okay, so we have this dimension of A plus B by B equal to dimension of A by A intersection B. So in the previous video, I have already explained you about dimension. I have explained you about this dimension of V by W. Okay, V by W is equal to dimension of V minus dimension of W. So using this formula, or using this we'll get here as dimension of A plus B minus dimension of B, which is equal to same applying here also. So we get dimension of A minus dimension of A intersection B. Okay, now you bring this one to this side, we get dimension of A plus B equal to dimension of A plus dimension of B minus dimension of intersection B. So which is our required result. The next question, if V is a finite dimensional and W is a subspace of V, we are taking W to be a subspace of V, then we have to prove that we can find a subspace W1 of V such that V can be written as W external internal direct sum W1, and dimension of V is equal to dimension of W plus dimension of W1. So I am taking here the dimension of V to be n. Now since this is a finite dimension, W is also a finite dimensional vector space. Okay, so I take dimension of W to be m with the condition that m is less than equal to n. And the basis of W I'm taking as W1 till Wm to be the basis of W. Now since this is a basis, these are linearly independent. Okay, now these are linearly independent sets and it is present inside V, so it can be extended to form the basis of V. Okay, it can be extended to be a basis of V, so this will be the basis of V. I'm taking this, I'm extending this linearly independent set to become the basis of B, so this becomes the basis of V over F. Okay, now this is the basis of V. So we'll try to define a mapping from V to W as F of any element here can be written as a linear combination of this basis element. So we have this. This is sent to an element in W. So any element in W can be written as a linear combination of this basis element. So we have this. Okay. Now we want to show that this F is a linear transformation. So we'll try to prove that F is a linear transformation. So we'll take two elements from V. So the elements in V look somewhat like this. So we have here summation I equal to 1 to n lambda I Vi Wi sorry the V2 equal to summation I equal to 1 to n beta I Wi. So we have this as the element of V. So we'll try to prove that F is a linear transformation. So we'll add these two. So we have F of V1 plus V2 is equal to F. We put the value of V1 and we put the value. So summation we can take common. We add the coefficient of this. Okay, so we have alpha I plus beta I Wi. We take Wi common. Now by the definition of the mapping, this is sent to summation I equal to 1 to m alpha I plus beta I Wi till m only. Okay, so this is an element in W. So this can be separated as this. If we reverse back the definition here, so this can be written as F summation I equal to 1 to n alpha I Wi plus F summation of I equal to 1 to n beta I Wi. So this is nothing but v1, so we get here v1. This is nothing but v2, we get here v2. So this is f of v1 plus f of v2. Now I take an element from the field and I take one element from the vector space. Then we have this. Any element in the vector space can be written as this, where lambda I belongs to the field. Now we have to take here f of alpha v. I have to show that it is alpha fv. So I took f of alpha v. So alpha v is this. So I multiply this alpha inside. So we get alpha lambda I wi. So this, by the definition of f, this can be written as this. By the definition of f, here I'm applying the definition of f. So this can be written as summation I equal to 1 to m alpha lambda I wi. Alpha is a scalar. It will come out of the summation. So we get summation I equal to 1 to m lambda I wi. So if I reverse the definition here again, so I'll get here f of summation I equal to 1 to n lambda I wi f of alpha fv. So this is nothing but v. So we get f of v. So we have shown that f is a linear transformation. Now we'll try to show that it is onto. Okay, so I take one element in W. Okay, then any element in W can be written as this. So by using the reverse of the definition of f, I'll have this. So this is an element in V. So we have f of v star, where v star belongs to V. So that shows that f is onto. So we have shown here already f is onto. Since f is a linear transformation and f is onto, we can apply the fundamental theorem of vector space homomorphism or linear transformation. So by using this, we have the vector space. So here the vector space is V divided by the kernel of f is isomorphic to the vector space. It is isomorphic to the subspace W. So we have here isomorphic to this. Now let us find what is our kernel. So kernel, we take an element. This is the definition of kernels. I take one element in V such that f of v should be 0. So f of this is 0. Okay. So this, by the definition, we have that this is equal to this. Now w1, w2, till wm are the basis of W. So they are linearly independent. So since this set is linearly independent, the scalars should be 0. So we have here the scalar equal to 0 for all I equal to 1 to m. So we get all the scalars till m it is 0. Above m we cannot say. So till m it is 0. So this v, now v can be written as a linear combination of the basis of v, that is w1, w2, wm, wm plus 1 till wn, I think wn. Okay, so only till alpha m it is 0, others are not 0. So this v can be written as now summation I equal to m plus 1 till n alpha I wi, such that v belongs to W. We know now, we know already, we have done in the previous, I have already proved that kernel is a subspace of V. So we have proof here, kernel is a subspace of V. We know already, I don't need to prove. Now this kernel F I'm taking as W1. So I donate this W1 to be kernel of F. Then we have this, I take one element in V. Then this element can be written as a linear combination till n. So this I can separate into two. So we get I equal to 1 to m till, then from m plus 1 till n. So this is an element in W and this is an element in W plus. So any element in V can be written as a linear, means an element in W plus an element in W1. So I have to just show now the intersection of this. It means intersection of these two subspaces is 0. So I took one element here where it belongs to both. So since it belongs to here as well as it belongs to here, so it can be written as a linear combination of this as well as it can be written as a linear combination of this. Both are V. Okay. So both are V. So this should be equal. So we have this equal. So bring this one to this side. We get minus lambda I. This lambda I take as alpha I. So this become as summation I equal to 1 to n alpha I wi equal to 0. But this W1, W2, Wm plus 1 till Wn are the basis of V. So these are the basis of V. So this set is linearly independent. Since the set is linearly independent, the scalar should be 0. So we have here alpha I equal to 0, and this I will be running from 1 to n. So after that, if I put here alpha I values to be 0, then I get V to be 0 in both the cases. So we got that V should be only 0 element. So the intersection of this consists of only 0 element. Okay, consists of only 0 element. So that shows that this vector space V is the direct sum of W, internal direct sum of W and W1. Okay, now we also have this isomorphism by fundamental theorem of vector space homomorphism. We can also have this isomorphism, that is V by W1 is isomorphic to W. So since this is a finite dimension vector space, this is also a finite dimension vector space. So the dimension of this should be equal to this. So we have this. So this we have already proved in the previous one. So dimension of V by V minus dimension of W equal to dimension of W. So bring this one to this side, we get dimension of V equal to dimension of W plus dimension of W1. Thank you.